Well, hello ap1. We should be recording, and I'm recording right now with my new microphone. If I've got the microphone placed properly, we should minimize the amount of clicking sounds we hear. So we should minimize the amount of clicking. There will still be some, I'm sure, but hopefully there's less. At any rate, we're going to be talking today about the equation of continuity and more in general about fluids in motion. So before we get started, let's look at your textbook on page 289. And what we want to look at is the top here. We need to look at these assumptions. What we're going to be doing is assuming an ideal fluid. An ideal fluid is a fluid that is non-viscous, meaning there's no internal friction between the adjacent layers of the fluid. The fluid is incomprehensible. I'm just kidding, it's incompressible. It means that its density is constant. We're not going to be changing the mass of the fluid. The volume of the fluid will also not change. The fluid motion is steady, and the fluid moves without turbulence. There'll be no eddy currents or any such thing. And you can read more about those concepts in the textbook here. So back to our video, and hopefully less clicking. So the equation of continuity. This involves fluid movement. The easiest way to visualize this is fluid moving in a pipe, water moving in a pipe. So let's just start with that. Here we go. We have some pipe, and the pipe has a small end and a very large end, let's say. Okay, so there's our pipe. We are going to have fluid on this side is going to be at a cross section A1. By the way, this pipe is just a section of a pipe. The pipe continues. The pipe continues on this way and continues on this way. You have to imagine the fluids traveling through the pipe to get to this part. The fluid will leave this pipe and move onwards into the next part. I'm just showing you a cross section of pipe where the two areas change, okay? So we have area 1, and on this side we will have area 2. I'm going to move a specific volume of fluid on this side at area 1, and the claim is that the exact same volume of fluid will move over here. And we're going to look at that continuity. We played with this in Pascal's principle, by the way. You remember with the small piston, we made a small force through a very large displacement, and then that area, small area, and that large displacement gave us some volume. Well, on the other side, with the large piston, it had a large area, and we got a very large force but a very small displacement. That large area and that small displacement gave us the same volume. Anyways, we're exploring a similar thing here. Alright, so we're going to imagine the fluid is going to move this way with some velocity. The same fluid will move up that way with some other velocity too. We're going to assume that the volume of fluid, let's just make ourselves a displacement here. So let's say that that is my displacement for fluid 1. So all of this stuff right here is going to be fluid 1. Okay, and then fluid 2, we're going to make, there's fluid 2's displacement, so a much smaller displacement and a larger area. Okay, so what is our continuity going to look like? Well, we know the fluid entering area 1. The fluid entering area 1 is going to travel a displacement delta x1. Right? It's going to travel through some displacement, and by doing that I'll get some volume. And just to remind you, in case you forgot, that displacement will relate to the velocity in that way. Okay? Now we also know the mass of an area 1, the mass of that fluid that enters the pipe is going to be equal to density times volume. Agreed? I don't know why I asked, you guys can't answer anyway, so hopefully you agree. So let's see. The mass entering at area 1 is going to be equal to density times volume, right? Well, volume is area times displacement. So there's my mass, density times volume. Now remember, displacement displacement is velocity times time. So my displacement is velocity times time. Cool. Well, I could make a similar argument for the amount of fluid, for the mass of fluid that actually leaves on this side. I'm going to make the same argument for the fluid leaving this side. And we're going to say that the mass of that fluid is going to be the density of the fluid times the area times the velocity of that fluid times time. Now, because the fluid is not changing mass or density or anything, we know the mass of fluid going in the pipe at one end is going to be the same as the mass of fluid coming out the other side, so I can equate those two. So I can say that that has to equal that, which leads us then to say that density area 1 velocity 1 times time has to equal density area 2 velocity 2 times time. And since the density is the same for both, and if I push on it for 3 seconds on one side, it's going to move for those same 3 seconds on the other side, so that cancels, and that gives us our continuity equation. That the cross-sectional area of the pipe of the fluid times the velocity of the fluid has to remain constant. This quantity cannot change, it's the same. You can think of this as the volume averaged time, the volume per time if you want. Area has the units of meters squared, velocity has units of meters per second, which gives us meters cubed per second. That is volume per time, continuity, volume. Questions, comments, concerns? Again, I'm kidding, you can't ask questions right now, but you could probably write a question down in your notes and ask once the video's over. That would be a thing. Alright, so we have now explored the motion of the fluid through a pipe that changes diameter. Well, this brings us to Bernoulli. Bernoulli is going to have us deal with a situation where a pipe is not only going to change diameter, but it's going to change elevation. Uh-oh. So here's my pipe, and it's going to change elevation, and it's going to change size. And here's the ground. So let's draw ourselves a picture of this pipe, label a few important pieces, and we shall talk. Let's call this height y1. Let's call that height y2. Let's say we're going to have fluid with velocity 1 there, and the fluid is going to come out this side with velocity 2. Let's have displacement 1. And remember, we have a much smaller displacement over here, so we'll have displacement 2 right there. And nextly, let's say that we have coming in on this side force 1, and coming out that side, and I drew that backwards, and in this direction we're going to have force 2. So I got force 1 coming in this way, and this is the force that's going to push all the fluid here through the pipe, and force 2 I'm saying is going that way. This will be more clear in a second, but think about it that to determine the net force, we're going to have me pushing on the fluid, but the fluid over here is going to be pushing back. As I try to move fluid through the pipe, the fluid in the pipe over here is going to be in the way. So as I push here, the fluid here is going to give a reaction force, and those two forces are going to combine to be the total force. Okay? Alright, so let's analyze this. The amount of work done at section 1 of the pipe, at the beginning of the pipe, to remind you, these are all the ones, so we're referring to this end first. So the work done at area 1 on the fluid is going to be force times displacement. The force is going to be the pressure at that side times the area at that side, and the displacement would be displacement 1. Okay? Now, area times displacement is volume, agreed? So the work at 1 is going to equal the pressure at 1 times the volume. Now the volume, I'm not going to label it as section 1 or section 2 because we just learned that the volume is going to be conserved. So the amount of work is just going to be the pressure times my volume. Now, oops. I'm going to make a similar argument for the work at the other side. This is the work being done by the oppositional force. This is the work that's being done against me. So this is the water sort of working against me, the water in the pipe that I'm not moving, that I have to push out of the way to move the water that I'm moving. This is my reaction force. This is going to be negative P2V. And again, I'm making the same analogy that force is times displacement gives me work, force is pressure times area, area times displacement gives me that volume. So we get this equation. And this is working against me, so that's taking energy out. I dump a bunch of energy in, some of that energy moves my fluid, some of that energy is lost pushing other fluid out of the way, okay? So, the net amount of work being done, is the work being done at 1 plus the work being done at 2. Which means that the net amount of work being done is going to be P1V minus P2V. Cool. Now, if we look at this, we know that work can be written another way. If we remember from last year, this is me drawing a line so we can go into the way back time. Last year, we said that the net amount of work done would just be any change in kinetic energy plus any change in potential energy. And to remind you, kinetic energy has to do with the energy associated with motion. Potential energy in this case has to do with changes in elevation. In this case we mean gravitational potential energy. And we've just seen from previous examples that fluid flowing through a pipe with a change in area is going to experience a change in velocity, which means it will change kinetic energy. And in this example, we are actually changing elevation, so there's going to be additionally a change in potential energy. So this is where Bernoulli comes in. How do we accomplish all this? Well, we're going to take these two expressions for work and equate them. That's what we shall do. So I'm going to say that P1V minus P2V equals any change in kinetic energy plus any change in potential energy. Alright, so let's expand this out. Oh boy, get ready for some mathematics. P1V minus P2V equals change in kinetic energy. Well, that's going to be 1/2 mv squared, but we're talking about mv1 squared minus that'll be 1/2 mv squared minus actually I should do this way, I'm forgetting myself here. mv2 squared minus 1/2 mv1 squared. I'll explain here in a second, I can't write and talk. Alright, remember changing kinetic energy is going to be final minus initial. We're starting at the 1 and we're moving towards the 2, so final minus initial, okay? And that's the change in kinetic energy plus the change in potential energy. Well, the change in potential energy is going to be final minus initial again, so mg y2 minus mg y1. So there's my final minus initial. So there's my equation. Well, let's do some more algebra. I want to divide everything by these velocities. I have velocity there and there. I'm going to divide everything by velocity. So that term, all of this stuff I'm going to divide by volume. I said velocity, dummy, that's volume. So pressure 1 minus pressure 2 equals 1/2 mass. I'm dividing by volume and I get velocity 2 squared. Before I continue, I want to point out something. Mass per volume is density. Okay? So when I divide this by volume, I get mass per volume, I get density. And that's too much, so I'm going to write that smaller. So I'm going to get 1/2 rho v2 squared minus 1/2 rho v1 squared plus rho g y2 minus rho g y1. So I've divided this term, this term, this term, this term, and this term by volume, and I get density, 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 density. So you can think of this as the volume averaged kinetic energy, and you can think of these as the volume averaged potential energy. And these are our pressures. The next thing to do is notice that we have a bunch of 2's, and then we have a bunch of 1's. And I'm going to collect them on these appropriate sides of the equation. So doing that, we have P1 plus 1/2 rho V1 squared plus rho G Y1 equals, I'm not going to write them all out, what the heck, P2 plus 1/2 rho V2 squared plus rho G Y2. And that is Bernoulli's equation. A simpler way to write it is that pressure plus the volume averaged kinetic energy plus the volume averaged potential energy is constant. Any of these terms can change. However, the sum total of all of those terms remains constant. When I have fluid flowing in a pipe that experiences different sizes in diameter and changes in elevation, it will always be the case that the pressure, the kinetic energy, and the volume average potential energy sum together to remain constant. This is Bernoulli's equation. The next thing we have to do is work a couple of problems, and we'll